Today we will discuss about Unit 4. It has two topics. One is heat transfer. The other one is vibration. Okay, these are the two topics. So first we will discuss about heat transfer problems. So how to solve problems related to this heat transfer. When you go for heat transfer, again, we can divide a problem into two categories. One is one-dimensional problems, 1D problems. Another is a two-dimensional problems. So when you go for 1D, similar to your bar element, here also you have an element which is having two nodal points. So one element will have two nodal points. Okay, this is the only one element we have in 1D. When you go for 2D, you have a triangle element, just like a CST element. So something like this. So something related to a triangle is having three nodal points. First, let us concentrate problems related to one-dimensional problems. And you know that, let me consider this is a bar element. So இது ஒரு bar element anda, what is your stiffness matrix K? Can you tell me? Can anyone tell me what will be the stiffness matrix K?
AE by L 1 minus 1 minus 1.
Yeah, very good. AE by L 1 minus 1 minus 1 1. Okay, so you know that A indicates your cross section area, L indicates the length, and E indicates your Young's modulus. Okay, so இதுவே வந்து heat transfer problem na இந்த E க்கு பதில் K. Okay, this has to be changed. So which means I will write it here. Your stiffness matrix K is nothing but AK by L. AK by L 1 minus 1 minus 1 1. So this is the only difference here. Okay, so where K indicates what is your conductivity for that particular material. Okay, so structural problem now, so we call it as Young's modulus. So that is your material property. So when you go for thermal problems, instead of Young's modulus, material property, instead of Young's modulus, we will consider conductivity. Okay, so you have conductivity matrix related to that. Okay, so since it's a one dimension, the conductivity is 1. So you don't have a matrix here. So just we will write it as K, right? So this is your terms. So again, this one-dimensional problem, you can be classified into three different types. Three types. So what is the three type? One is pure conduction. Other one is convection only at the end. And third one is convection for the overall particular element. Okay, so like a fin problem. So if I consider this one dimension, okay, let me consider this a cantilever beam or something like this. So one side you have a high temperature, other side you have to identify a temperature without any convection. Then that is one type, pure conduction. Next, conduction and convection at the ends. Third, fin problem, like you have convection everywhere. So you have convection here and also at these points. Okay, so we have more convections here. So this is your fin type of problem. These are the three different types related to this. Okay, so let me show it here. So this is only pure conduction. That is what we discussed. So one element we have two nodal points, 1 and 2, and the displacement functions are T1 and T2. So T1 and T2 are the outputs. So as I told you, you have an input and an output. So இப்போ வந்து ஒரு 1D structure problemல input வந்து force னு சொல்லுவோம், output வந்து deflection சொல்லுவோம். Your input is your heat Q1 and Q2 and your output is your temperature. So T1 and T2. Okay, so this is a pure conduction. Okay, so it is Kc. Whenever you indicate suffix C, indicate it's a matrix related to conduction. Okay, so before we start with your convection, so first I have to clarify one thing. If you have a conduction, you have only stiffness matrix K. Okay, so whenever you have a conduction, you have only stiffness matrix K. So if you have a heat transfer, if your data is having some heat transfer K, so they are given Q, what Q value. In that case, you don't have the stiffness matrix. Instead, you will have a force matrix. F. So, but if you have a convection, so convection has both. So you have stiffness matrix and also your force matrix. So stiffness matrix or force matrix. Okay. So these are the terms. So it depends on the problem. Okay. So now let me go for convection. So conduction and convection. You can able to see that this is my body object. So you have conduction and you have convection only on this end. In the end the convection. In that case, as I told you, conduction, you have two matrices. So you have stiffness matrix also. First, the conduction mattum paathukom. Conduction matrix is this. Okay, so A K by L, 1 minus 1 minus 1, 1. Okay, so but when you go for convection, convection ku stiffness matrix tani matrix. So convection ku tani matrix. What is the convection matrix? It is HA 0001. Yeah, inga 1 potrukko. Can you guess? Because it is at the nodal point 2. So this is, if I address this, oh, this is 1 2, this is 1 2. Okay, so 2 2 la you have this convection. Okay, that is why it is like this. For example, if you have convection only here, okay, not here, okay, only in this position, then what is my stiffness matrix K? So K will be different. What is the matrix? HA, it is having 1, right? So 1 this is 1 0 0 0. Okay, this is my term. So whenever you have convection on both sides, it is KH is equal to HA 1001. That's it. Okay, so don't divide by 2. It is not divided by 2. That is applicable only for force. Okay, so when you have force, as I told you, so in the first case, another you have convection on this side. Second case, you have convection on both the sides. Okay, so when you have first case, so already we have this convection on this side, right side. Okay, so if you have convection on left side, so what is my force matrix? So my force matrix FH will be H infinity TA. So HAT infinity. Okay, HAT infinity. This is 1 0. Right? It is 1 0. So in the force down on the divide agum. Okay, so the stiffness matrix divide agade. So here, if you have convection on both the sides, what is my H? FH will be H T infinity A divided by 2. Inga than divided by 2 potukono, inga 1 1. So add panna HAT infinity 1. Okay, so not here. So here only it has to come like that. Okay, so the problem, it depends on whatever category it is. So left side la convection, right side la convection, rendu side convection. You have to consider the matrix and we have to solve the problem related to this. Now we will proceed with one problem. We complete that problem as quick as possible. Then I will explain the same by using ANSYS software. Now we will proceed with this particular problem. So what it says, you have a wall of 0.6 thickness and its thermal conductivity is 1.2 watt per meter Kelvin. And you have another wall which is 0.06 meter thickness and its thermal conductivity is 0.3. They also mentioned what is the inner temperature. Inner temperature is 1000 degrees centigrade. Okay, and outside it is insulated and it is exposed to air. So you have a convection of 35 watt per meter square Kelvin and its temperature is 30 degrees. Okay, so first let us write what are the given data. Okay, so in this, I will call this as 1 and this as 2. In that case, K1 I know, so K1 is 1.2 watt per meter Kelvin and K2 is 0.3 watt per meter Kelvin. Okay, so and you know what is the thickness L1? L1 is around 0.6. This is 0.6 and this is 0.06. Next, you have temperature T1. So how you call it as a T1? We convert this as an element. When I convert this as an element, what we'll do? We will going to consider an element like this. So you have two elements. One element is having nodal point 1 and 2. And other element, element 2, which is for this portion, it is having nodal point 2 and 3. Okay, this is my particular thing. So now T1 is given. So in that case, this is one nodal point 1, right? In that case, they mention what is your T1 value. So my T1 is 1000 degrees centigrade. Okay, and they also mention what is the heat transfer here. So what is your convection in nodal point 3, which means I will call it as H3. Okay, so nodal point 3 representing nodal point 3, which is equal to 35 watt per meter square Kelvin. And you know what is your T infinity related to that. My T infinity is 30 degrees centigrade. Okay, these are my datas. So to solve this, what are we going to do? We are going to consider two elements. So this is my first element, and this is my second element. We will solve one by one. So let me consider element 1. If I consider element 1, you have two nodal points, nodal point 1 and nodal point 2. Okay, and this is my element 1. So there is no convection in this element. Okay, so since there is no convection, so we have only K matrix related to conduction. So you have only pure conduction here. So you know what is the formula. So conduction is AK by L 1 minus 1 minus 1 1. Okay, right. So you need this data. What is my A? They are not mentioned anything about A. So let me consider A is equal to 1. There is no data. Next K. So K is for element 1. So what is the element 1? It is already identified. We mentioned this K1. K1 is 1.2. So this is 1.2. What is my L? L is the length of my element. Length of my element for this is 0.6. You know that L1 is 0.6 because we are concentrating only on this particular region. So it is 0.6. So we have the data. Let us identify what is my K value. Let us identify what is my K value. But whenever I write this K value, I have to mention what is my addressing. So this K is connecting nodal point 1 and 2, right? So I will write it here. So 1, 2. Okay, so indicating that this is my connection. So this is equal to 1 into 1.2 divided by 0.6. So this is 1 minus 1 minus 1, 1. Can you tell me what is the value for this K12? We're getting 2.
Yes, sir.
So I am bringing this 2 inside. So in that case, my matrix will be 2 minus 2 minus 2. Okay, this is my first element. My first element is over. So when you go for element 2, for element 2, you have this element which is connecting nodal point 2 and 3. You have convection at the end. Okay, in that case, you have conduction matrix K for conduction, which is, you know that it is AK by L, 1 minus 1 minus 1, 1. You also have convection matrix KH. So since you have convection on the right hand side, it is HA 0, 0, 0, 1. Okay. Other than this, since you have a convection, you have force matrix also. Force matrix for convection, which is equal to HA T infinity 0, 1. These are the data. So I want to identify all these matrices one by one. So let me identify what is A for this location. Again, it is not given, so it is considered as 1. What is my K for this particular thing? So for second region, my K is 0.3. Okay, so K2. So it is 0.3. What is my L? For my second region, my L is 0.06. So it is 0.06. So let us identify what is your KC. Okay, so when I say KC, I am going to mention it is 2, 3. It is connecting nodal point 2 and nodal point 3. So this is equal to A. A is 1. A K divided by L. So L is 0.06. 1 minus 1 minus 1 1. So now what I go, we can just substitute that. So we'll put the 5 inside. So my 5 minus 5 minus 5 and 5. Okay. Next we'll go for K. Again this 2 3. This is related to H. This is related to C. Okay, this is conductivity stiffness matrix. This is convective stiffness matrix. For convective, you know H into A. My H is, they mentioned, H data they given as 35. So it is 35. A is again we consider as 1. So this is 0, 0, 0, 1. Okay. So I will rewrite this. So I will call it here again K 2 3 is equal to, this for H is equal to, what is my matrix? 0, 0, 0, 35. So now we have one more matrix, which is my force matrix. What is my force matrix? F. F is H A T infinity 0, 1. This is my force matrix. So in that case, force matrix at location 2 3 is equal to, you know what is your H? H is 35. Area I don't know, it is 1. So you consider as 1. T infinity is your atmospheric temperature, which is 30 degree. So we'll consider 30 degree. So this is from 0 to 1. So can you tell me what is your force 2 3? You're getting around 1050, right? 0, 1050. So this is my overall matrices. Now we completed identifying what are the elements. Next thing is I have to assemble it and I am going to proceed. So you know that F is equal to K into T here. So usually we call it as U. So but that is a structural problem. This is a thermal problem. So we call it as T, temperature. Okay. So what is my F? F is a matrix. Same. So you have to identify what is the size of my global stiffness matrix. How many nodes we have? We have 1, 2, 3 nodes. So each 3 nodes has each node is having 1 degrees of freedom. So 3 into 1, which is equal to 3. So my global stiffness matrix size will be 3 cross 3 matrix. So in that case, so this is my global stiffness matrix F is equal to K into T. Okay. So when I address this, so how to address this? So you know that this is my location 1, nodal point 2, and nodal point 3. Similarly, this is 1, 2, 3. Similarly, here also I will call it as 1, 2, 3. Similarly, this is also 1, 2, 3. When you address your matrices one by one, so this is element 1. It is connecting nodal point 1 and 2. So I will call this 1, 2 and 1, 2. Right? So, and this is element 2 is also, it is connecting nodal point 2, 3, 2, 3. And this is also nodal point 2, 3, 2, 3. And your force matrix is also connecting nodal point 2, 3. So this is related to 2, 3. Okay. So let me connect this. So 1, 2 is 2 minus 2 minus 2, 2. I'll put it here. So 1, 2 is 2 minus 2 minus 2, 2. Next, let me go for element 2, 2, 3, 5 minus 5 minus 5, 5. Where is my 2, 3? So this is my location 2, 3. So plus 5 minus 5 minus 5, 5. We have one more, which is your convective matrix. It is 0, 0, 0, 35. So it is 3, 3 alone. This will be 35. So 3 cross 3 will be here. So this is plus 35. Okay. So others will be zeros. So these terms are zeros. So this is 0 and this is also 0. Let me assemble my force matrix. You know that there is no force in element 1. So nodal point 1. This is 0. So force matrix is only applicable for this one, 2, 3. So 2 is also 0. 3 is 150. 0. This is 1050. Sorry, 1050. Next up is your temperatures. So you have T1, T2, T3. So in our question, they mentioned only your T1 data. So temperature at this location, it is 1000 degrees centigrade. In that case, we consider only 1000 degrees centigrade. So this will be 1000. Okay. So this is T2 and this is T3. Okay. So one thing is, whenever you have a value here, don't use that particular row to solve the problem. Okay, you will get error. So since the unknowns are in 2 and 3, you go for 2 and 3 equation to solve the problem. Okay, so this temperature problem, you can't strike it out. There is no possibility of striking it because it is not 0 here. When it is 0, you can strike it out. Since they have a value, you can use as an equation only. Okay, so I'm going to use it as an equation. So first equation, so second equation, this one. Okay, second row, I'm writing as an equation. 0 is equal to minus 2 into 1000, which is minus 2000. This is 7, right? 7 into T2. So plus 7 T2 minus 5 T3. In that case, I will write as 7 T2 minus 5 T3 is equal to 2000. I'll call this as equation number 1. We go for the other one. So nodal, so your 3. So this is 1050 is equal to 0 into 1000. Okay, it is 0. So remaining minus 5 T2 minus 5 T2 plus, so this is 40, right? 40 T3 plus 40 T3. Okay, so this is, we call it as, right? I will write it again. So minus 5 T2 plus 40 T3 is equal to 1050. This is equation number 2. So can you solve this 1 and 2 to identify what is your T2 and T3? So solving 1 and 2. 3, 34.314 degrees centigrade because we substitute only in degree centigrade. Okay. And T3?
68.03.
8.039.
Okay, very good. So 68.03 degrees centigrade. So these are my values. Okay, so let me proceed. Now in ANSYS, so let us consider the same problem. We will try to solve it and we will plot a graph. So how this is moving. Okay, so we go for preferences. So go to thermal, click OK. So then we'll go for preprocessor, element type, add. I'm going to consider this as a solid element. So I will choose solid 4-node element. I'll click OK for this. So this element doesn't have any thickness, so no need to worry. Let it be, there is no real constant for this. So directly go for material property. When I go for material property, let me add material models. So thermal, conductivity, isotropic. So first conductivity value, first conductivity is 1.2, right? So we'll go for 1.2. Okay, so this is 1.2. Okay. Again, we'll go for material, new model. It is asking ID2. Let me choose that. Again, I will go for isotropic. Go for the second conductivity. What is the second conductivity? So I think it is 0.3. Okay, we'll proceed with 0.3. So go to 0.3. Click OK. So now, so since we are solving in 2D, so we have to model it. So I don't know what is the height of the element. You choose any height. It doesn't matter because the plot will be same. Let me go for modeling. I go to create area. In that, I will go for a rectangle by 2 corners. In this, my x, y is 0, 0. Width is 0.6. The first one is 0.6. Height, I don't know. Let me consider 0.1. Okay, it's because it will be always constant. So this is my first particular shape. This is for the element 1. Okay, let me click OK, apply. So now second one, I have to start with 0.6. I have to start from here. Okay, that's why I am going 0.6. Otherwise, you can also click here. If you click here, it will show you what is my value. Then you can change the other values. So 0.6 and 0. My width is 0.06 now. And my height, it should be constant. So previously I given 0.1. So this is also 0.1. Like this, then click OK. So I got this area. So I got 2 areas now. So now to transfer data from this area to this area, you should not add these 2 areas. Instead, you have to glue it. So in your area, so you have operation in your modeling, you have operate. In operate, you go for booleans. In boolean, you go for glue. So don't go for add. When you add, what happens? These 2 area become a single area. Okay, don't do that. So go to glue option, select these 2 areas, this and this, then click OK. Now the data can be transferred. Okay, this one is over. Let me go for meshing now. Go to mesh. So go to mesh attributes first. Click default attribute. In that, make sure your element material property is 1. Material number is 1. Because 1 is 1.2, 2 is 0.3. Okay, that's why. So let me consider this material property number is 1. I click OK. Now go to mesh tool. Make sure you select smart size. Bring it to fine. Click mesh. Select the first one alone and then click OK. When you do that, so it shows a window which is showing only your elements. It is not showing the area. So once this is done, you go to plot. Again, plot areas. I click plot areas. So it shows both the area. Now go to default attributes. Change your material number 1 to 2. Change your material number to 1 to 2. Click OK. In your mesh tool, don't change the settings. Let it be same. Click mesh. Select the second area and then click OK. So that will mesh automatically. So now it has been meshed. It shows the entire component. So your pre-processor is over. So only thing is I have to apply the load. So go to solution. You go to apply, define load, apply thermal temperature. Okay, in temperature, I'm going to apply what is the temperature on this side. So the temperature on this side is 1000 degrees centigrade. So go to temperature on line, select this line. So this is 1000 for the entire thing. Click OK. Select temperature. This is 1000. Click OK. So I apply a temperature here. The other one is convection. So go to convection, on lines, select the right hand side part, click OK. In this, my film coefficient is, I think it is 30, right? 35. My heat transfer coefficient is 35 and air temperature is 30 degree. Okay, so let me proceed. So heat transfer film coefficient is 35 and bulk temperature is 30 degree. Specify this and then I'll click OK. So now this part is also over. So I applied temperature and convection. Only thing is I have to solve it now. Let me go for solve current load step. Click OK. So your solution is done. Let me check with your solution. So go to general post processor, read results first set. So this is applicable only for latest ANSYS. So otherwise you will get the result directly. So I have to click this first set. Now plot results, contour plot, nodal solution. In this, go to DOF temperature, nodal temperature. So you'll get what is the temperature difference. Okay. So the minimum temperature is 68.03. I think we achieved around that particular 68.03. So we got the same answer. Right. So now, as an additional part, what I can do, I have to identify what is the temperature across this entire path. Okay. So how to do that? if you want to go for that, you go here. So in your general poster, you have something called as path operation. Go to this path operation. I'm going to define a path now. Click define path. It has all the locations. So whether I have to give in terms of location or in terms of my nodal points. Since I know the location, this point is 0, 0, right? And this point is 0.6 plus 0.06. It is 0.66. Are you getting it? Right? So I think this is 0.6 and this is 0.06. When you add this two, it is 0.66. Okay. So that is this location. So I go for define path by location. It is asking what is my path name. Let me type this. This is temperature plot, temperature path. It's up to you. You can give any name. So I'm going to enter only 2 points. So I'm going to mention 2. How many data sets I want? So it is up to you. I want 50 data sets. Number of divisions also. Let me consider it is 50. Okay. So just this is the enter for that particular line. It takes 50 data. Okay, that is what it means. And we click OK. Now it is asking what is my path point number. So first point is 1. It is like drawing a line. Okay, I'm going to draw a line from this location to this location. That's it. So my coordinates are 0, 0, 0. That's it. Let me click OK. Now it is asking second line, second point. Second point is 2. And my X location is 0.66. So first I have located this one. Now I am locating this point. Okay, it is 0.66. Others are 0. I click OK. So again, it is asking one more point. You will cancel. So 2 points is enough. So to define the path. Any doubt up to this?
No, sir.
Yeah. Now, once your path is located, now what I can do, I can go to plot paths like this. It shows there is a plot. So temperature path is here. Okay, just to show whether it is there or not. Okay. Next is I want to map. So what this path has to be. So this path has to be in terms of temperature. So you have map onto path like this. So just select temperature. Okay, so you have different options. So I want only temperature. Let me select temperature. Okay, in the path the temperature எனக்கு வேணும். So I am selecting that. So map onto path. அதில் வந்து temperature select பண்ணி okay கொடுத்துக்கிறேன். Okay, that is over. Next, plot path item னு ஒன்று இருக்கு. So below this. So just click a plus sign. So whether you want a graph or a geometry, something like this. I want a graph. Okay, let me click this. So இதில் what I want temperature. Okay, so just select temperature, then click OK. So now this is my temperature plot. Okay, so this is the distance from 0 to 0.66. And this is your plot. I think I can fit. No, this is the maximum fit. Okay, so now you can able to see the maximum temperature is 1000 degrees centigrade. So up to this is your first particular material. So it is around 347.627. So what is our answer? Our answer is around 334. There is a small difference. Okay. So after that, I don't know whether this one may be accurate. So because there is a very, very small difference. After that, it is decreasing a lot. And at the end, it is around 68.039. So that is my overall plot. So this is how the temperature is distributed along this particular domain. So thank you all.